Right, so our next speaker is Marc-André Peuf. He's a PhD candidate at Johannesburg, Gutenberg University, Maine. His master's thesis was in cooperation with IBM Research about analyzing file create performance in GPFS parallel file system. His studies about studies with IBM Research further investigates tracing techniques in parallel file systems. He's the maintainer of GeckoFS distributed burst buffer file system in collaboration with Barcelona Supercomputing Center. Overall, his research interests focus on file system storage, object store, and system analytics.
Okay. Thank you for the introduction, and also thank you for the organizers of this wonderful lab workshop here. Again, my name is Marc Peuf. I'm a PhD student at the University in Mainz and in the group of Andre Brinkmann. And we have been involved in the past in a number of different research things with lustre, for example, the token bucket filter, but also LPCC. And today I want to talk also a little bit of a different talk, where we talk about what we're currently doing, where our research is going at the moment. And at this point, we're looking into concurrent write support for the persistent client caching that we have. And yeah, let's go. So first of all, I want to do a little bit of an outline because we're touching on a number of different topics. Firstly, what we want to do and what we have been doing in the past years is we looked into ad hoc storage system. This is where the GeckoFS that you just heard in the introduction comes into play. And I want to present this as an example and how we can potentially use this in the persistent client cache and lustre that's based on the HSM. Then I want to also talk about the limitations that both the ad hoc storage systems have on a broad, in a general sense, and then what the LPCC limitations have and how we can combine all of these together. So if we look at the cost of using the parallel file system, this is something that we have seen at the Barcelona Supercomputer Center. This is in this case not a lustre, but a GPFS, but we've also seen this in Mainz, where we have a lustre, is basically that if we would run the same workload over a week at different points in time, we have different performance that the user sees, and it can be in orders of magnitude difference. So we have a huge variety in I/O performance, and of course the applications suffer from the PFS load. They don't really know what performance they're going to get and how much time they should allocate for their job. So, of course, the other thing, and we've heard this also for the persistent client cache, is that we have these node local storage SSDs available on the nodes, but they're not really used by the applications themselves. So one of the things, of course, here is in the motivation that we want to exploit the whole I/O stack, and we want to reduce the data movement. For example, if we have only data that is, only used within a job, but not later written out to the storage system, or is not supposed to written out to the storage system, then it doesn't make sense to write it down to the parallel file system. So in the end, improve data locality and do work where the data actually lives. So what we have nowadays is that we have the situation where the applications are running directly on the parallel file system and we have uncoordinated access. So every application is kind of doing what they want. Node local storage is typically ignored, and we have these variability that you've seen earlier on the slides. So what we want to do is we want to actually have that all of the applications are basically only running on the node local storage, and then in the end we can, in a more sequential sense, write the data back that is actually or should be persisted on the parallel file system. And if we have the appropriate schedulers here, we can have this, or we can do this in a way that is most suited to the parallel file systems. So if we have a lot of random I/O, have a lot of file creations, these can then be absorbed by the node local storage, and therefore we have reduced the parallel file system contention, reduce the variability, and at the same time for applications who actually need to use the parallel file system for whatever reason, they also benefit from that because some of the load is taken away from it. So one of the things that we want to do, and this is where the ad hoc storage system come into play, we want to basically use the SSDs that are available there and put them together so we can use the performance and the capacities of these SSDs together, and in the end, hopefully achieve linear scaling the more nodes we have. And here I want to talk a little bit about the research that we have been doing and that is still ongoing. which is the GeckoFS verse buffer file system, as an example of what we want to use later. But again, this is just a stand-in and could be any ad hoc file system like BGFS beyond and so on. So for GeckoFS, the core challenges that we wanted to do, we wanted to have a file system which is of course very fast, because if it's not fast, then there's no reason to use it, right? So we changed a little bit about how the file system internally behaves, so that we have no central control components, we have no global locking, and therefore can achieve the linear scaling with the number of nodes. The next part is, if such a ad hoc storage system is deployed, it is also very important that this happens very fast. You cannot spend minutes at the beginning of a job to just start this ad hoc storage system, because it's first of all very expensive. So for GeckoFS, for example, we can do a deployment in about 5 seconds on 512 nodes. The third part is we wanted it to be completely in user space. So that means the user can do whatever they want. They can start up the file system, they can use it, and there's no administrative support necessary. So, and the admins don't even need to know about it, except that now suddenly the node local storage is used. And finally, all the storage that is available to the user, it could be memory, it could be the SSDs that are available on the nodes, should be used by that file system. And also a fast network fabric should be used efficiently with RDMA and everything that comes with it for OmniPass and InfiniBand. So to give you a quick look on the architecture that we have built, this is important later to understand how that works. So basically what we have here is that the application is using just normally the libc library to use all their I/O calls, and then what we do, we intercept these I/O calls with LD preload. But not the normal LD preload, but we do it with a system call interception library from Intel, so that we only really intercept the system calls and not fwrite, for example. And then what we're basically doing, then we are in this user space library, and then we just distribute it across all servers. And we do this with a high-performing RPC framework that is created by the Argonne National Labs. That's called Mercury. And on the server end, that is called the daemon here. We store the metadata in a RocksDB, which is also stored on a local storage system, on a local file system. It could be ext4 or XFS or any other, where also then in the end the data is stored. And of course, before the GeckoFS can be used, you would need to stage in and out the data at the beginning and the end of the job. So how does that look like? If we look at the performance that we had in the beginning, where we looked at the I/O variability of GPFS, and this is basically the same plot, now with GeckoFS included here, and of course, because there's no variability, there's no congestion on the nodes, you have very linear scaling. And we did this up until 512 nodes. We're showing here the 32 nodes, up to 32 nodes, and it's very predictable for the user. We can also look at the metadata performance. In this case, apologies, in the top right, it shouldn't say GeckoFS versus BGFS, but versus lustre. This is at our Morgan II supercomputer at the University in Mainz. And in this case, we wanted to look at the benefits that such an ad hoc storage system has compared to the parallel file system. And in this case, we weakly scaled this GeckoFS file system with 16 processes per node, with 100,000 files per process, simply with MD test, up to 512 nodes. So in the end, we have over 800 million files, and we get close to 50 million creates per second. We also compared this here with lustre, but of course, in this case, it is a smaller installation for this specific file system, so we only had a single MDS and a single MDT with just a couple of hard disks in the back, and there, of course, it plateaus off very, very quickly. For the GeckoFS, we ranked fourth in the IO 500 10-node challenge in supercomputing 19. Nowadays, there's a different file system at the top spot. It's called MadFS, but it's very much inspired by GeckoFS, kind of recoded in Rust, but the algorithms are very much the same, and they're using a different network library, which is very interesting for us, because it shows that our architecture also works on much faster clusters that we have available at the university. So now, what is the problem? Why don't everyone uses these file systems? Now, these file systems are not transparent to the user, and they really require user interaction. Not only with starting and stopping the file system, you could achieve this very simply with Slurm scripts, Prolog and Epilog, but you would also need to stage the data in. And in that sense, there's currently a Euro HPC project running called Admire, where we want to specifically look into this. This is from a collaboration with 14 European partners from Spain all the way to Poland. But it's basically about adaptive multi-tier data management with a focus on computational and I/O malleability. That means, for example, an ad hoc storage system can be on a number of nodes, and while the application is running, we just expand the number of I/O nodes. And at the core of this project architecture, we use ad hoc storage system, not just GeckoFS, it's also ad hoc storage system from the University in Madrid as well, but also from the Barcelona Supercomputing Center. Since DDN and the University of Mainz is part of this project, there's also an idea of actually combining the benefits that the persistent client cache in Lustre has with the ad hoc file system. And now I want to go a little bit back about what the HSM actually brings and what PCC actually brings for those who are not aware. But in the end, the takeaway here is it's somewhat difficult to actually use them in real life. So for the hierarchical storage management, I think this figure floats around for over 10 years now, but basically it is a framework for tiered storage, typically archiving, where we can move the data to tapes, for example, while the metadata still resides in Lustre. And if we have an I/O operation that would happen on a file that is currently on the tape, then we would automatically trigger a flashback. So it's very user transparent. There are a number of components here, the MDS coordinator, the client agent, and the POSIX copy tool that we heard earlier today that kind of coordinates these archiving and restore operations. Now this HSM is then used for the Lustre persistent client cache, and this motivation and goals for LPCC is very similar to what we have with the ad hoc storage systems. Node local storage isn't used by anyone, by the users that is. And the goal is, of course, to increase the I/O performance and decrease the I/O interference. But in this case, because it's directly working with Lustre, it is transparently included. So the drawback that we have in the ad hoc storage system is here solved. For the features, LPCC can maintain a global namespace, and we have basically two caching modes. One is read-write, and one is read-only. At the moment, read-write cache in Lustre for LPC is only for a single client, and read-only is actually for multiple clients. So how this looks like from the architecture, this is from the paper that we worked on together with DDM and OneCloud here, is basically you have the MDS and the MDT with a coordinator where the file 123 here is actually stored on the node local storage, and then the actual data is no longer there on the OSTs, and the client can directly use the node local storage system here. And in this case, the LPCC has actually an HSM copy tool and agent running to archive and restore the data. If you look at the performance here, this is also from the paper where different workloads were run. One is just simply with IOR, the other is an HPC benchmark, HACC, where Lustre and PCC is compared. And of course, based on the installation that they were having here, Lustre plateaus at some point, but the PCC implementation, of course, linearly scales with the number of nodes because they are only using the storage and has no interference. So what are the limitations then? LPCC offers caching only in the context of a single node. That means for read-write that if multiple nodes want to cache the same resource, that is not possible, and then we have a fallback to the normal Lustre way of working directly on the parallel file system. So there's no parallel I/O from many nodes possible. For read-only, multiple nodes can cache the same resource if they're opened in read-only mode, but it leads to redundant data. It's not that the data is distributed across all nodes, they're actually duplicated. And if hundreds of nodes are doing that in certain workloads, that can then, of course, also lead to I/O overhead here. And finally, if you have a file that is bigger than the node local storage here, the SSD, then of course you cannot save it because it simply doesn't fit, and the I/O performance is also restricted to the storage. For metadata, It is a little bit more difficult. As far as we know, you can create a file there, but you still have to talk to the metadata server to create it. So you have a bottleneck here for creation. But then the consecutive stat operations, for example, are cached. But in general, ad hoc storage systems, now we come back here, can offer a solution to this limitation because we already have these right striping of having linear scaling for metadata and data workloads, regarded if you have a shared file or a file per process, random or sequential I/O. So when we started this, so then a naive coupling approach is just if we look at that, by the applications using the Lustre client and PCCs using the node local file system, we could just replace the node local file system with a distributed ad hoc storage system. That would be very nice, except that this is a huge coding overhead, right? Because you need to change many, many things. The logic that we have for read-write and read-only caching in PCC must be largely rebuilt. There's also the question, what would happen if a remote node is accessing this data that is currently on an ad hoc file system? How do they get the connection, and so on? There might be little benefit for metadata workloads, specifically for creation of files. And then, of course, this all must be tested. So there's just in general a lot of coding overhead and complexity in here. There's also the concern that this is maybe a little bit too specific for a general Lustre ad hoc file system approach. We might be able to get it to work for a specific file system like BGFS or GeckoFS, but not for all. So overall, this is not a satisfactory solution. So our proposal, and again, this is very much work in progress. We haven't tested this or really built this yet. But what we're currently thinking, this is why we are eager to hear your feedback, is instead we want to build on the existing Lustre HSM mechanisms, do somewhat similar to LPCC, maybe also include some of the LPCC's components, but largely avoid extensive Lustre modifications so that the solution can more or less stand on its own. It should be semi-transparent, not as difficult to use at ad hoc storage systems, but there's also some user interaction involved if you use LPCC, and this would be kind of the same here. And then we can also include something that we've learned when building GeckoFS is how we can use the interception layer here. And in the end, the goal is, of course, the compatibility with any distributed ad hoc file system. So how would that look like? If you have a compute node with a Lustre client and a distributed ad hoc file system running, this is how it would look like today. And then you also have this interposition decision library here. And the purpose of this library is basically just to say, well, should this specific file be cached, then it would go to the ad hoc file system. If it's not cached, then it would be just a fallback to Lustre. So how that would work, as a proof of concept, what we're trying to build, is that first of all, a user or a Slurm Prolog script would register the HSM, normally as you would also do it in LPCC, without release. So we do not want to actually delete the files that are currently on the OSTs, simply because you have more nodes involved here for a distributed ad hoc file system. And if one node fails, you already lose your data. This is kind of the purpose of the ad hoc file system. We don't really have the persistency here, but there should always be the fallback here for Lustre. The next part is that then the application will use LD preload again and uses this interposition decision library, which already knows what files should be cached. And there can be some communication between Lustre and this decision library here. And then once the application is doing an I/O request, like a write on a specific path, this decision library would then decide, should I forward this to the normal Lustre or to the ad hoc storage system? For staging data, for now, we are looking into that the distributed ad hoc storage system has kind of the responsibility of getting the data lazily when it is needed. But we also would like to include some of the work that has already been done in LPCC, like prefetching, use of the copy tool or the policy monitor. And then finally, of course, if there's a conflicting access happening, similar to what LPCC already has, then the data should be flashed back immediately to Lustre. And why is this the case? Simply, we do not want to have this ad hoc storage system for the complete compute cluster. We want it, for now, basically only for a specific job or at least user, right? So this flashback still needs to happen. So if possible, then the next steps after this could be a future kernel integration. So of course, we already know with GeckoFS, these interposition libraries can cause issues. And we've seen this already for most applications that works fine, but there are some issues here. So a kernel-based solution is always preferred, also for transparency for the user, of course. So our idea is to move this decision library to the kernel as a shim layer or a pseudo file system in between the VFS and lustre, which would look like this. So it's basically the same idea, which is no longer in user space, but now in the kernel, in which then this shim layer decides if it should forward the request to an ad hoc file system that is in the kernel or any other. Could be GeckoFS, could be BurstFS that is developed in the US, or Hercules that is developed in Madrid, for example. Okay, so to conclude, we have basically two solutions here. We have LPCC, and the drawbacks here is that we do not really have a concurrent write caching across multiple nodes. The ad hoc storage system provide that, and on the flip side, the ad hoc storage systems solve this distributed concurrent write support, but they are not really easy to use and they're not transparent. So the idea is to combine them and hopefully get a better result here. And the discussion here would be, of course, and I'm happy to talk to you in the break about this as well, is what pitfalls do you expect here to happen? Because there's a lot of things that obviously can go wrong. What would your requirements be to use such a systems, also from an administrator perspective? And what are the typical use cases you see? There are already a bunch of use cases for ad hoc storage system, of course. It could be deep learning applications, checkpointing applications, and so on. And that is this. Thank you very much. And now questions.
Question, James.
Yes.
First question is Git repo for this?
Yeah, for GeckoFS?
Yes, for all this work. Do you have it available?
Okay, so again, we have GeckoFS available. It doesn't seem to be the last slide deck, but yes, we have a Git repo available for the work that we want to do here. We don't have anything public yet. We have very much started the work. We very much know already how this interposition library would work, but the communication between the lustre client and the distributed ad hoc storage system about how to stage data around, that is not, we're not finished yet.
Okay.
Yeah.
Second question is, for the shim layer, why not fuse?
Well, it is in a sense very similar to fuse, but at the same time, you have to, well, we had this discussion a couple of times in the end. And we also know that if we, for example, have a GeckoFS with fuse, it would be very slow, simply because of the number of context switches, the back and forth between kernel files, right? So the idea is what we want to do in the shim layer is a little bit different than what fuse does. First of all, we don't need fuse if we have a kernel-based file system like BGFS. We can just call it directly. But if you have something like a user-space file system, we are looking of another way how this could communicate with user space. It can use the fuse device, but it could be a little bit different. So we're not yet finished on the decision. If some parts of fuse we could use, but we are quite sure that we will not use fuse simply because the other user space file system would need to include that as well. So we would like to keep them the way they are.
Okay, thank you.